All right, let's start. As I was saying, we are going to continue from where we left in our last class. The topic that we are going to cover, the main topic that we are going to discuss in today's lecture is finding complex roots of numbers. And that number doesn't necessarily need to be a real number. It can be a complex number. It can be real or complex. So how do we do that? Generally, for example, if you are given a number, say, for example, 4, and you are to find the square roots of 4, generally, this is a misleading. Sometimes we get confused with this symbol. This symbol actually means only 2, not -2, right? -2 is root over -4, but sometimes we write this symbol as a shortcut for square roots of 4. In those cases, sometimes we prefer to write like this. This can be misleading. That is why I'm going to avoid ambiguity. I write the elaborate form, that is square roots of 4 are 2 and -2. Similarly, cube roots of 8 are, this is interesting because the only cube root some of you may found for 8 is actually 2, but since we are dealing with cube root, you can think of the equivalent problem of finding the solutions to the equation x cube equals to 8. Just like the previous one can be written as an equivalent that states find the solutions to the equation x squared equals to 4. And the solution for this equation, we have two solutions, 2 and -2. Similarly, since this is a cubic equation, we must have three solutions. One of those three is 2, but what about the other two? And the answer is the other two are actually complex numbers. And this can be seen as follows: x cubed. We can rewrite the equation like this, and then we factorize using the formula of a cube minus b cube to get x squared plus twice x plus 4. This part gives x equals to 2, which we already know, and this part gives x equals to -2 plus minus root over 4 minus 16 by 2. This actually gives -2 plus minus 4 minus 16 is -12, right? So considering -4 as 2 root I, 2i, we can write basically 2 root 3i by 2. So we got three solutions: 2, -2 plus root 3i by 2, and okay, this can be further simplified, right? So -1 plus minus root 3i. So two of those three solutions are here, and the remaining one is the one we already found at the beginning of our discussion. So so basically, our discussion in today's lecture is limited to finding these two guys, right? But we are going to face problems once we increase the degree of this equation here. For example, if you are to find the roots of, for example, x to the power 5 minus, find a number which is to the power 5 of some known number. 2 to the power 5 is 32, right? 2, 4, 6, 8, I mean 16. No, not really, 32. So let's try to find the roots of this guy. We haven't even started our discussion of finding roots of complex numbers. We are still limited to finding roots of real numbers, but yet you can understand that this equation is pretty difficult to solve, right? So, and I can just keep increasing the order of this polynomial to make problems even much harder to solve. What about x to the power 100 minus 2 to the power 100 equals to 0? That would be pretty difficult to solve, right? So we have to find a smarter solution so that that solution can be applied to problems of this sort, and that problems doesn't get harder if we keep increasing the power here. And that method actually works for both real and complex. So let's let's think of the generalized problem. Solve the equation. Basically, we are dealing with the problem. Find the nth roots of some complex number z, which is of the form, of course, sum a plus ib. This problem can be rearranged. I mean, an analogous problem can be formed that sounds like this. Solve the equation x to the power n equal to z, right? Okay. In fact, we are not really fond of x when we are dealing with complex variables. So to make things look like how we usually see, I'm preferring to write a not here to denote that this is some constant complex number. And I'm preferring to write z here, which is a complex variable. So this guy is a variable, but this guy is some constant complex, right? How do we solve such problems? That's our main discussion topic in today's lecture. So z to the power n is z naught. Now, say for example, z naught, when converted into the polar form, looks like this: r e to the power I alpha. So just for convenience, okay, let's discard the idea of convenience. So technically, z can be written as, in the next line, the nth root of r e to the power I alpha whole to the power 1 by n. So here we can just write r to the power 1 by n and e to the power I alpha by n. But I want to modify things a little bit. In this manner, you are going to get just one root actually. But we need to find n number of roots because there are n number of nth roots, right? So how can we do that? Try to visualize that if I just add a 2 pi here with alpha, this doesn't hamper the equation actually. So let's write like this. Let's write another equation, equal sign, and the expression is actually equal to alpha plus 2 pi. This is because e to the power I alpha plus 2 pi is actually e to the power I alpha times e to the power I 2 pi. Keep e to the power I alpha intact and expand this guy using Euler's equation, which should be cos 2 pi plus I sine 2 pi. And sine 2 pi is 0 and cos 2 pi is 1. Cos 2 pi is cos 0, right? Which is 1. So this is just e to the power I alpha. That is why I can write like this. In fact, if you observe a little further, you will see that if I write any integer multiple of 2 pi here, this also satisfies the situation because any multiple of 2 pi, if you take cos, you are going to get 1. And if you take sine, you are going to get 0. So I can just add an integer k here as I wish. So k is any, for now, say any integer. Whatever integer you put here doesn't matter. The equations remain true. Now, when I write like that, I have to moderate the equation here, right? So I times alpha plus 2 pi k, so that here I get I times alpha plus 2 pi k divided by n. Now you can see that I have already applied, I mistakenly removed the 1 by n here. I think I mistakenly removed a bracket closing also. So So basically, I have applied the Euler's equation, the De Moivre's equation, because whenever I write some e to the power I theta to the power n equals to e to the power I n theta, I actually mean I wrote cos theta plus I sine theta to the power n equals to cos n theta plus I sine n theta. So even though you cannot really see it directly, but you actually use De Moivre's equation here. So this is a situation where Euler's equation and De Moivre's theorem are both in action, right? Now, here is the thing. If you keep putting values of k equals to, say if you put k equals to 0 in this equation, you get exactly to the power I alpha. Okay, I think we must write by n here as well. All right. So if you put k equals to 0, you are going to get e to the power alpha by n, which should have been the case if I did not add these 2 pi k here, right? So this is the base case. Now, keep putting positive integer values. What happens for a moment, I have to attend a very important call. I'm sorry for that. Let's get back to where I was. As I was saying, if you observe the function e to the power I theta, which is actually cos theta plus I sine theta, as you know, the time period for cos theta and both of these functions, sine theta and cos theta, are periodic, right? And the time period for both of them is actually 2 pi, which means e to the power I theta is also a function which happens to have a time period 2 pi. Basically, this is exactly what was demonstrated here, right? That it's basically a periodic function of time period 2 pi. That is why if you keep increasing k up to n minus 1, you are going to get different values. But the moment you put k equals to n, this part becomes 2 pi, which means we are exactly back to where we were when we put k equals to 0. So putting k equals to 0 and putting k equals to n is equivalent. And putting similarly, if you put k equals to n plus 1, this is going to be equivalent to putting k equals to 1, which means I actually do not have to put any further values of k once I reach k equals to n minus 1. That is why I'm removing all of these to avoid any confusion. So in such cases, whenever while solving a problem you reached up to this point, you write this statement explicitly that the value of k is actually 0, 1, 2, etc. up to n minus 1 and no further. And we do not have to care about negatives as well, because those are going to be case of repetitions also. So now all you have to do is put all these different n number of values of k to get different n number of roots. Let's demonstrate the idea using a real example. For example, let's solve the case where z to the power 5 equals to 32, the one I wrote earlier. So 32 can be written as 2 to the power 5. And 2 to the power 5 is simply 2 to the power. If you think of it as a complex number, you can express it in the polar form like this, where the argument is actually 0. So then you have to write like this: 2 to the power 5 times e to the power I, 0 plus 2 pi k. Now, writing 0 is redundant, right? So let's just discard the 0 to write I times 2 pi k, so that our situation gets simpler here. The expression becomes simpler because we had 0 here. This is not going to be the case for every problem, of course. Then what is z, which is the fifth root of 32? Is simply 2 to the power 5 e to the power I times 2 pi k whole to the power 1 over 5 equals to, this is just 2 e to the power I times 2 pi k by 5, where this is where we write explicitly what k is. K is going to be 0, 1, 2, 3, and 4, and no further. So if you just denote all the roots by the index k, so basically we can write like this: k and zk. We can make a chart if we want. You can present this in any way you want. If you put the 5 possible values of k, 0, 1, 2, 3, and 4, you get z0, z1, z2, z3, and z4, 5 complex numbers, of which the first one is going to be, if you put k equals to 0 here, basically this is the expression for zk we are using, right? So putting k equals to 0 just gives 2, the real number value. Real numbers are also special cases of complex numbers. And z1 is 2e to the power I 2 pi by 5, which you can express in a plus iv form as well. This is going to be 2 cos 2 pi by 5 plus I into 2 sine 2 pi by 5. And you can just simply write all the numbers here in a similar manner and fill up the chart, right? And each of those complex numbers can be expressed in this a plus iv form as well. This is doing the same job repeatedly. That is why I'm omitting the. I'm not really doing the rest of the calculations. Should be understandable to you. Now, what if z is a complex number like this? 1 plus root 3 I. So basically, and what if we need to find the fifth root of 1 plus root 3i? So the original problem may sound like this: find all the fifth roots. Let's write a smaller number of roots. So all the third. I mean, by third, of course, I mean cubic roots of 1 plus root 3i. So this is the question, and in the solution, the first thing you are going to assume is z to the power 5 is 1 plus root 3. But the overall method works for polar cases, right? That is why we need to express this number in the polar form. So modulus of 1 plus root 3i, we generally express this by the letter r, right? This is root over 1 plus 3, which is 2. And the argument is tan inverse root 3 by 1, which is just pi by 3. So this should be 2e to the power I pi by 3. Then again, we are going to express this equation like this: 2e to the power I times pi by 3 plus 2 pi k. Okay, 5 is not the one that I should write here. Rather, I should write q since I changed the question. So therefore, z is going to be 2 to the power 1/3 e to the power I should write pi by 9. In our last example, it was 0, but now we are not so lucky. The expression is slightly more complicated than the previous one. So 2 pi k by 3, where we write k equals to 0, 1, and 2, because n is 3 here. Now, you can understand this guy is itself the, not really. Okay, so we express this by zk, of course, and you do not really have to make a chart. This is just how I am representing the roots. The chart is not necessary. You can just calculate in a straightforward way. So z0 is simply 2 to the power 1/3 e to the power I pi by 9, which of course again you can write cos pi by 9 plus I times 2 to the power 1/3 sine pi by 9. So z1 is 2 to the power 1/3 e to the power I. You have to, okay, now k is 1, so 2 pi by 3 is here, which means 6 pi by 9, 6 pi plus pi, 7 pi by 9. I have to write 7 pi by 9 here, if I have not made any mistake. So this should be 2 to the power 1/3 cos 7 pi by 9 plus I times 2 to the power 1/3 sine 7 pi by 9. The final root should be z2 equal to 2 to the power 1/3 e to the power I. I have to add another 2 pi by 3 here, so that 6 pi by 9, 6 and 7, 13 pi by 9. which is 2 to the power 1/3 cos 13 pi by 9 plus I times 2 to the power 1/3 sine 13 pi by 9. Now, here is an interesting thing. You should be able to see that we are in the argument side, we are actually dividing an interval of 2 pi into, for this particular problem, for example, we divided the 2 pi interval into 5 equal parts. So technically, if you plot the zk's, that is all the complex roots in the complex plane, we are going to see an interesting pattern. For example, for k equals to 0, the root is z0, which is 2. Now, all of these roots must have modulus equals to 2, of course, as can be seen here every time. The modulus is constant, only the varying part is the argument. And this should be the case because if you take modulus on both sides of this equation, you are going to see that modulus of z is a constant, and which is 2. So technically, all the roots should be on this circle of radius 2, that's for sure. But what are the arguments? What happens here is you are actually dividing the interval from 0 to 2 pi into 5 equal parts. So 360 degrees by 5 is exactly equal to what? 72 degree, right? So what you are going to get is another 4 roots. Overall, the 5 roots are going to be on this circle of radius 2, and they are going to be spaced angularly 72 degrees apart from each other. So 72 degree, roughly 72 degrees here, another 72 degree is 144, which is somewhere here possibly, and another 72 degrees, 210, 216, which should be somewhere here, and the other one should be somewhere here. So the overall circle is going to be divided into 5 equal slices. Same is going to happen here as well. So what happens is we are dividing the 2 pi interval into 3 equal parts. And you can see that the modulus is constant 2 to the power 1/3. So probably 2 to the power 1/3 is here, but the first root is not here in this example. In this example, the first root is z0, which has the argument pi by 9. So this is pi, divide that by about 9 to get something like this. So this is where z0 should be, somewhere around here. We are sketching just roughly. This is not an exact plot, right? So where should z1 be? 7 pi by 9. So technically 120 degree apart, because 360 by 3 is 120 degrees. So about 120 degree apart, somewhere around here, I think. If this was 9 instead of 7, it was going to produce e to the power I pi, then the root would be here. So in our case, we are going to get somewhere close to pi, but not as large as pi, some angle. And of course, the other root is going to be somewhere here, which has the argument 13 pi by 9. So we are going to get 3 roots angularly deviated by 120 degrees from each other. This is Z1, this is Z2. Please let me know if there is any confusion anywhere so far in our lecture. All right, if that's the case, then let's solve some problems on whatever we learned about complex numbers. For example, the first problem is, let's use another. Show that tan inverse 1/5 is nearly or very close to or nearly equal to pi by 16. This is a pretty interesting problem. And of course, you cannot just calculate tan inverse 1/5 from calculator and show that it's almost very close, almost equal to pi by 16 by showing that their difference is pretty small number. You cannot do that. You have to do some analytical solution here. So this is what we can do. Look at this number, and we know that generally, if this is the argument of a complex number, then the complex number is going to be 5 plus I, right? So technically, we are dealing with the argument of the complex number 5 plus I. And what is 5 plus I? You can see that the modulus of 5 plus I is root over 5 square plus 1 square, which is root over 26. And say the argument theta is what we are trying to approximate here, which is tan inverse 1 by 5. Then this number is going to be root over 26 times cos theta plus I sin theta. Now, this is what we are going to do. We are going to take 5 plus I to the power 4. Now, if you take square of this, you are going to get 26. Now square again to get square of 26, which is 676. And we have cos 4 theta plus I sine 4 theta. Originally, we had a power here, but we used, of course, you can understand, we used de Moivre's theorem. Now the question is, why did I take the power, especially the number 4? The reason is, look at this particular angle. This angle is not one of those standard angles we are used to using in solving problems by hand. But if you multiply this particular angle by 4, you're going to get pi by 4, which is a standard angle. That is why we want 4 theta here. I'm going to show that 4 theta is almost pi by 4, which would mean theta is almost pi by 16. That's my target. So what we can do is, this is what we are going to do. Take the power 4 of 5 plus I. This is, at first, this is 25 plus 2 into 5 into I, which is 10I, plus I squared, which is minus 1. I just squared, so I have to square again. And the right-hand side is same. So this is just 24, I think, plus 10I whole square. The right-hand side remains same. Take the square now. 24 square is, I think 25 square is 525. So 24 square should be what? 625 actually, 625. So this is actually 4. Okay, what is 24 square? So 4 4s are 16. Okay, we can do this trick actually. So this is 625 plus 1 minus 50. So 626 minus 50, this is going to be 476 actually. So we have 476, I mean 576 actually. So we have 576 here, plus 2 into 240, which is 480 I, minus 10 square, which is 100, because I square is minus 1. The right-hand side remains same. So finally, the simplified expression is in A plus IB form. 476 plus 480I is exactly 676 cos 4. Basically, I do not really, I think I do not really need the cos plus I sin form. Rather, let's just write the polar form, e to the power I times 4 theta. So this number has argument equals to 4 theta, and that 4 theta is actually tan inverse. Okay, let's write like this. Instead of dealing with tan inverse, let's just write this. This means tan 4 theta is simply y by x, which is 480 by 476. 480 by 476. Now this number is actually dangerously close to 1, right? The denominator, both of numerator and denominator are large numbers with a difference of only 4. So this means this is pretty close to 1, which means I think you got the idea that we are almost done with the problem here. So this just means 4 theta is pretty close to pi by 4. Therefore, theta is pretty close to pi by 16, which was the claim that we needed to prove in this problem. Please let me know if there is any confusion anywhere. Otherwise, let me move on with another problem. Let me choose a problem. Let's solve this problem. If cos alpha plus cos beta plus cos gamma is equal to 0, and similar for sine alpha plus sine beta plus sine gamma is equal to 0, then prove that two ideas actually. One is cos thrice alpha plus cos thrice beta plus cos thrice gamma is 3 times cos alpha plus gamma. And number 2, the sine version of the same equation. So sine alpha plus thrice alpha thrice beta plus thrice gamma is 3 times sine x beta plus gamma. Okay, this is the problem we're going to solve now. How do we do that? Okay. You can understand that initially you cannot see any sign of any complex number anywhere. This looks like a trigonometry problem from the first look, of course. But if you see that these two guys and these two guys can be paired like this: cos alpha plus I sine alpha, cos beta plus I sine beta, and cos gamma plus I sine gamma, so that we can involve complex numbers. And say, for example, this is just A, this is just B, and this is just C. Then from the given two equations, if this equation is equation number 1 and if this is equation number 2, so 1 plus I multiplied by 2 gives us just A plus B plus C equals to 0. Now, this is the only reason behind this is basically we did not involve complex number just because we have cos alpha and sine alpha, etc. But also the original given information involves the angle alpha, beta, gamma. But the one we are going to prove, the equations we need to prove involves thrice of the angles, right? And whenever some multiples of angles are involved, intuitively, you should be able to see why the polar form, not just complex number, but their polar form specifically, can play a very important role here. That is why we introduced complex number forcefully from intuition. So what we have is A plus B plus C equals to 0 here. Now, you have a formula A cube plus B cube plus C cube. This is a pretty interesting and pretty famous formula. This is actually equal to A plus B plus C into A square plus B square plus C square minus AB minus BC minus C. A pretty useful formula in basic algebra, right? So if A plus B plus C equals to 0, then a cube plus b cube plus c cube minus 3bc is going to be 0 times this whole thing. And whatever the value of this whole thing is, doesn't matter. The result is going to be 0, which means a cube plus b cube plus c cube equals to thrice abc. Now, why is this equation playing a role here? Because this equation involves cube of ABC, which would produce the thrice of the angles, right? So a cube is simply, if you cube on both sides, since the modulus is 1 on the left hand side, basically modulus of ABC all are 1. So this is just straightforward use of De Moivre's theorem to get cos thrice alpha plus I sine thrice alpha, which is a cube. Then b cube is cos thrice beta plus I sine thrice beta. And finally, c cube is cos thrice gamma plus I sine thrice gamma. And whatever the right hand side? The right hand side is basically the product of ABC times 3. So multiply all three of them. So if you multiply all three of them, you are basically, this is interesting because you have a 3 here, and instead of multiplying them in this a plus ib form, think of them in polar form. So this a is actually nothing but e to the power I alpha. Similarly, b is actually e to the power I beta, and c is e to the power I gamma. So multiply them to get e to the power I times alpha plus beta plus gamma. So that the right hand side is actually 3 times cos alpha plus beta plus gamma plus 3 times I times sine alpha plus beta plus gamma. So now all you have to do is equate the real part and imaginary part from left and right hand side. We can do that. Why we can do that? Let's see. If two complex numbers are equal, then you can do this. X minus alpha equals to I times beta minus y. Then square on both sides. You get a minus here. And then you take everything from the right and transfer them to the left to get this. Now, x, y, alpha, beta are individually real numbers. So we are dealing with real numbers only here in the last equation. And sum of the square of two real numbers can be 0 only if individually both of the numbers are 0. This is the only way. It is an well-known idea in mathematics, which means x is equal to alpha and y is equal to beta. So the left-hand side real part and the right-hand side real part are equal. Similarly, the left-hand side imaginary part and the right-hand side imaginary part are equal. So just take the real part on both sides of the equation to get cos alpha 3 alpha plus, I think I wrote alpha here mistakenly. So cos 3 alpha plus cos 3 beta and cos 3 gamma is equal to 3 cos alpha plus beta plus gamma, which is the first equation. And similarly, taking the imaginary part of the both sides, you get the second equation, which completes our proof. Please let me know if there is any confusion anywhere in this problem. Okay. So if there is no problem, then let's move on to another problem. Let's solve an interesting problem that involves finding roots. So the problem reads like this: find the roots of z to the power n equal to z plus 1 to the power n, and show that the solutions are collinear in the complex plane. Let's try to solve this particular problem. So we have z to the power n equal to z plus 1 to the power n. The first thing that you have to notice is if you somehow expand this guy to convert the whole equation in a polynomial in the variable z, it's not going to help for many reasons, but the most clearly visible one is that we do not know what n is. N is someone, but what is n, we don't know. Rather, you can just use the idea that the power on both sides is n. So we have z plus 1 by z whole to the power n equal to 1. So this is just 1 plus 1 over z whole to the power n equal to 1, which means 1 plus 1 over z. You can just rewrite this 1 on the right hand side as e to the power I into 0. And in the next line, just write it 0 plus 2 pi k, right? So we do not need to write the 0 plus again, of course. So what we are doing is using the idea of finding nth roots. So here I must have 1 plus 1 by z equal to e to the power I times 2 pi k by n. So now it's clearly visible why this method is helpful. I can just make z the subject of my equation. So 1 over z is e to the power I times 2 pi k by n minus 1. Therefore, z is 1 over e to the power I times 2 pi k by n minus 1. Now, actually, we successfully solved the problems. So technically, here you have to just write k equals to 0, 1, up to, do not forget to write this, of course. So we found all n number of roots of this n degree polynomial equation in complex variable z. And now for the last part, to deal with the last part, that show that the solutions are collinear in the complex plane. How can we do that? How can we prove that all these points are collinear? In the current form it is in, it's impossible to actually show this. So that is why what I'm going to do is write this in Cartesian form. So rather, I have another idea. I want to convert this into the Cartesian form, but to do that, my initial plan was writing cos 2 pi k by n plus I sine 2 pi k by n minus 1 in the denominator. Then the real part is cos 2 pi k by n minus 1. The imaginary part is I sine 2 pi k by n. So multiplication by conjugate would eventually give us the final result in a plus ib form. But I am now more interested in doing the same task, but in a more shortcut kind of way. So let's multiply by e to the power. Okay, let's use another color. Let's multiply by e to the power minus I sine pi k by n, both in numerator and denominator. So eventually you would get, after multiplication, we have minus I pi k by n, and initially we had 2 pi k by n. So the 2 vanishes to give us pi k by n minus e to the power minus I pi k by n. Why is this helpful? Because let's do a pretty simple calculation here. E to the power I theta is cos theta plus I sine theta, and e to the power minus I theta is cos theta minus I sine theta. Here is two basic, pretty fundamental but pretty simple and yet useful idea. Add both of the equation, e to the power I theta plus e to the power minus I theta would give you 2 cos theta. And similarly, if you just subtracted e to the power I theta minus e to the power minus I theta, the right hand side would be 2I sine theta. So the denominator here is in the form of this green color one, right? The formula is the green color one. So the denominator is simply 2I sine theta. We are not going to write theta here. Our theta is actually pi k by n. So basically, simplification becomes pretty shortcut here, right? And in the numerator, we just write cos pi k by n minus I sine pi k by n. So we started with z here, remember? So in the next page, therefore z is, let's rewrite what we got there again. So cos pi k by n minus I sine pi k by n divided by 2I sine pi k by n. So if you do the division, you get cos pi k by n by 2I sine pi k by n minus I sine pi k by n divided by 2I sine pi k by n. Simplify to get, here cos by sine is cot, and 1 over I is simply minus I. You can see that by multiplying I on both top and bottom. So I square is minus 1. So we have minus I. So this is just minus half I cot pi k by n. And here I have the i's gets cancelled. So minus half. And just that actually, sine also gets cancelled. So you can just take minus half as common to write 1 plus I times cot pi k by n. We did this only because to prove this collinear part, we were pretty clueless while we had this expression, but now you can think of some clue here. As you can see, real part, if this is expressed as zk, k standing for the index of different roots, then real part of zk is minus half. This is true for all k. And by k, I mean k equals to 0, 1 up to n minus 1, right? Which means in the complex plane, whatever the imaginary part be, real part of all these guys are actually equal to minus half. For example, if you put k equals to 0, cot 0 is what? Cot 0 is undefined. So maybe this is somewhere along, if you use the limiting sense, this is pretty close to somewhere here in the somewhere around plus infinity or minus infinity, but that doesn't matter. For different varying k, you are going to get different zk's, but all of those are going to have real part equal to minus half. So maybe, for example, this is maybe z5, this is maybe z6, this is maybe z7, who knows? But what we are guaranteed that these points are collinear, and that the line on which all these points are on is actually a line parallel to the imaginary axis in the complex plane, exactly my half unit to the left. So I made one mistake. I have to draw the imaginary axis to the right of this line, of course. And this value is minus half. And we are going to probably get, I don't know, it depends on n actually. If n is an even number, then at some point k is going to be n by 2. And in that particular case, we are going to get cot pi by 2 here, which is 0. That would mean we would get minus half, but it is never mentioned. The parity of n is never mentioned. N can be odd. And if n is odd, we are never going to get pi by 2 here as a multiple of as the angle inside cot, which would mean we are never going to get 0 as the imaginary part. So minus half may or may not be one of the roots, depends on the parity of or the oddity of n, right? Please let me know if there is any confusion understanding the problem. Okay, now we are going to, okay, there is a message. What if sine pi k by n? Okay, this is the question from one of the students. What if sine pi k by n is 0? I already mentioned the case actually. This means k equals to 0 is one of those cases, right? One of those cases where pi k by sine pi k by n is going to be 0. This would mean this guy is undefined. In that sense, that solution is undefined. But you can even think there is no mention of limiting ideas here. So there is no point dragging ideas of limit forcefully here. But if you can think of it like this, that as k tends to 0, z naught actually, basically zk tends to minus infinity, because you have minus half here. So technically, in a limiting sense, the point on this particular line, which represents geometrically the line x equals, okay, not this one, this line represents x equals to minus half in the complex plane. So there is one point at the bottom end here at negative infinity, and that point is also a solution of this equation if you include limiting sense. But the thing is, the set of complex numbers actually do not contain infinity, right? The extended you are going to be introduced to a special kind of set, for example, extended real number set. And extended real number set is actually the set of real numbers union plus minus infinity. So in this set, we treat infinity and minus infinity just like other real numbers. And that new set is called extended real number set. Similarly, if you apply the idea of extended complex number set, then that solution is actually acceptable. Otherwise, just in the set of complex numbers, that is in our case, in our course, we are just dealing with set of complex numbers, which is this capital C, right? In this set, infinity does not actually belong. So dragging this idea is unnecessary. That solution is not a part of the set of solutions of our given equation. So we do not accept the case where sine pi k by n equals to 0. And interestingly, just the topic, I mean, just because the topic came up, some of you are going to, I guess, study a thing called projective plane and projective line. Okay, so this is also a part of advanced analysis courses. So in those cases, we consider all the points at infinity in the complex plane as the same number. There are infinitely many points at infinity in the complex plane, right? In different, infinitely many possible directions. But in any of those directions, if you move up to infinity, you get to some point at infinity, accumulate all those points at infinity along all those directions. All of those points are going to represent the same number, infinity, in the idea of projective planes. So this is not a part of this course. That is why I'm discarding the ideas. Let's move on with what we have so far. Okay, now let's just, we have about, I mean, about 15 minutes. So use that 15 minutes to introduce another interesting idea about complex maps. Actually, in the book by Barnard and Child, you are going to see some topics like shifting in complex plane. For example, they use notations like this: capital Z is equal to small z plus a, or small z minus z naught. And this basically they meant that z is the old variable, capital Z is the new variable, and you are shifting the variable by z naught. So this is kind of a transformation of variables. And by shift, when you shift the variable, any geometric equation is also shifted. So if you had a parabola or a unit circle like this one in the complex plane represented by the equation, of course, modulus of z equals to 1. After shifting, you would get modulus of z minus z naught equals to 1. And eventually, the circle is going to look like this, with this point being z naught at the center, right? So there are examples of such simple maps or transformations in the book by Barnard, but let me teach you a more generalized idea. Let's introduce a transformation map f of z. And by an example, let me show you how this works. For example, your map is f of z equals to 1 over z. Most questions are like this regarding this topic, that what happens to some certain curve in the complex plane when you apply this transformation. For example, let's say, for example, the question asks what happens to some, probably, I think, the circle x square plus y square equal to 1 if the following transformation is applied. Now, you should be able to see that this is just actually the examples in the book, the ones like this are actually pretty easy transformations. This is just the same thing. This is just another example of a transformation, just a little bit more complicated than the simple ones given in the book, right? So this is the question. Let's try to solve the problem. So what we do is, let's solve the problem algebraically first, then explain the solution geometrically later. So write z as x plus iy, and maybe this is the output variable. So this is some other complex number, say u plus iv. So then different transformation is going to need different kind of calculations. The one I'm doing right now is actually the easiest mode of calculation to solve this particular problem involving this particular transformation. So x plus iy is 1 over u plus iv. Of course, multiply by conjugate to get u square plus v square at the denominator. So you have u by u square plus v square plus I into minus v by u square plus v square. So now you have we broke down the transformation equation into two different equations involving the real and imaginary parts, as if we are transforming coordinate wise, right? So u by u square plus v square and minus v by u square plus v square. Now the original equation in the xy plane was x square plus y square equal to 1. What happens if we just substitute x and y by these two expressions? You get u square by u square plus v square whole square plus v square by u square plus v square whole square equals to 1. So u square plus v square whole square and u square plus v square equals to 1, which means we have the equation of a unit circle again, which means what happens geometrically. Let me explain this part now. Geometrically, this is the input plane. We call this, say, xy plane, or in short, z plane. And this, we have two sets of planes actually, and this is, say, w plane. Why do we need two planes? One for the input side, which is z, and other for the output side, which is w. Technically, even though this looks like a single input, single output function, but inside it is actually 2 in 2 variable. There are 2 input variables and 2 output variables if we break them into a plus ib form, right? So in the z plane, the given equation was a circle, x square plus y square equals to 1. And in the output uv plane, you got the same equation again, u square plus v square equals to 1. But what if this was a square instead of 1? What if the radius was some other number than 1? What happened? What would happen then? Then we would get a square here, a square here, a square here, but you should be able to see we would get the right hand side equals to 1 over a square because u square plus v square is here. So this would mean if you got a bigger circle, which is x square plus y square equals to 3 square, then as its image on the w plane, we would get a smaller circle, u square plus v square equals to 1 over 3 square. So this is just a special case, a equals to 1, where the image under transformation remains invariant. But for other values of a, it's not going to happen. Now let's experiment a bit further with this particular transformation. First of all, let me know if there is any kind of confusion understanding what we did here. Okay, so let's modify our problem, and instead of a circle, let's find out, say this is problem number 1. Under the same transformation, we have a problem number 2. What that asks us to find the image when we transform this particular straight line, for example, y equals to mx. What happens then? Let's see. So we have this to help us. Now, if you, for this particular example, you have x equals to u by u square plus v square, y equals to minus v by u square plus v square. Now, if you, just for solving the y equals to mx problem, just divide y by x here. Then you'd get minus v by u. Then for y equals to mx, it actually means y by x equals to m, which means minus v by u equals to m, which means v equals to minus mu. So in this particular example, under the same transformation, if you have a straight line that looks like this, for example, y equals to 2x, the image of this guy under the transformation we considered is going to be y equals to minus 2x, or rather v equals to minus 2u. This is the z plane. This is the w plane. So basically, to realize a map geometrically, which is of complex variable, even though the input and output variable are singular in number, we had to use 2 set of 2D planes because technically we have 4 variables here, u, v, x, and y, and we cannot realize 4 dimensions. That is why we use the idea that we can just use 2 separate planes to represent input and output sides. And we studied how maps are transformed. But everything changes when you change this transformation function. This function can be simple like shifting, right? But this can be a function like this. F of z is, say, z bar. So this means, so again, u plus iv. So we have x plus iy bar. So we have x minus iy. So here x equals to u, but y equals to minus v. So you should be able to understand that straight lines are going to be transformed in a similar manner as they did in this example, because this equation that actually helped us to transform straight lines to another straight line is going to look similar once you divide y by x is equal to minus v by u. So straight lines are going to be transformed in a similar manner, but what about circles? So if you have a circle like x square plus y square equals to a square for this map under transformation of this map, let's call this another map G. So under transformation influenced by G, you are going to get a circle, replace u by x by u and y by minus v, you are going to get the same circle, and this is true for every a. So this time each circle is going to be transformed into the same circle. So there can be different kind of maps. For example, another complex map can be z square. And maybe you need to find the transformation of this hyperbola. So u plus iv is z square, which is x plus iy whole square. After squaring, you are going to get x square minus y square plus 2yxy. So you can see that in this problem, u is x square minus y square and v is 2xy. So u is x square minus y square and v is 2xy. And you can see that this equation just transforms into, under h of z, it transforms into just u equals to 1, which is a straight line and a vertical straight line, the one parallel to the imaginary axis. So this entire hyperbola, after going through this particular transformation equation, becomes a straight line. V was not even needed in this case. If you transform the let's write another hyperbola y equals to 1 over x. This becomes xy equal to 1. This becomes 2xy equals to 2, and eventually this becomes v equals to 2. So this hyperbola is going to transform into v equals to 2. So there can be different maps or transformations, and under that transformation, you can be asked to transform different shapes of curves in the z plane. So there are exercise problems regarding this topic. And of course, the problems in Bernard and Child's books are even simpler, as I said, because they do not introduce the idea of transformation in general, but rather they actually discussed ideas like rotations. I don't know if rotation was there, but translation was there for sure. So those maps are pretty straightforward basic maps. Please let me know if you have any questions anywhere from today's lecture. If not, then I'm going to stop the recording and end today's Zoom meeting here. Thank you for attending.